Okay, everyone. Hello. Welcome back. Good morning. We're very sorry about the technical difficulties. As always, internet difficult things. Okay. So, let's get started. This is the last lecture of the school. So, if you remember last time, we were talking about string theory, and we basically discussed how to think about the relativistic string. So now I'm going to do something one step beyond that. I'm going to talk about the quantum relativistic string, okay? So let me warn you now, this topic actually normally takes quite a long time, but I have to compress it into roughly 45 minutes. So what I'm going to do is, I'm going to at certain points ask you to just believe me when I tell you something, and that's just because we don't have time. Everything I want you to believe me for, you can really go home and check for yourself. It'll just take a while, okay? I'll try to motivate these things, but at different points today, I'm worried you will have to just believe me. And I apologize for that, but sadly, we have only 45 minutes or so. Okay, so let's get started. Quantum strings. Quantum strings. Just to recap, last lecture, we discussed how relativistic invariance, can be thought of as a symmetry that is not very different from normal rotational invariance, okay? And then I argued for you that there is a way to derive the following wave equation for the motion of a relativistic string, okay? Now remember, tau was time, sigma was a spatial direction along the string, tau was a time direction along the string, and x was the coordinate of the string itself. Now, also if you remember, I argued that we only get an equation for the transverse motion of the string because moving the string in the direction of the string itself makes no difference. So in particular, for every transverse direction, I runs only over the transverse directions, we get one equation of motion. And then I said the most general solution to this you can find from Fourier transformation. You do a Fourier transform and you get something of the following form. This is a solution to that for any values of these Fourier expansion coefficients an, okay? So you pick these an, and then the whole thing evolves in time in some way, given by these phase factors right here, okay? I think one thing I didn't do very carefully last time was, I'm saying here that there's an absolute value around the n here. This is useful for what's going to come later. It doesn't really make any difference if you put the absolute value there or not, and you can convince yourself of that by doing both expansions and checking. You just need to move the ANs around a little bit. Okay, and L string here, L sub s, was the overall length scale of a string. From your homework, you know this is roughly expected to be the Planck scale, and you know that's very, very small indeed. Okay, so today we're going to discuss the quantum string. Now the first thing, whenever you start solving any quantum problem is, you should ask yourself, do you really have to? Okay, because quantum mechanics is hard. Maybe you can just do the classical problem and be happy with that. So let me sort of explain to you why we have to solve the quantum problem by first talking about the normal simple harmonic oscillator. So everyone is happy with the simple harmonic oscillator, right? Okay, good. The potential for the simple harmonic oscillator looks like this. It's half omega squared x squared, where omega is the frequency of small oscillations. Throughout this, I'm going to set various things to 1. I'm setting, for example, the mass of the particle to 1 in this thing. I'll keep setting almost everything to 1 for simplicity from now on. Okay, so if we're doing classical physics, what is the lowest energy state of the simple harmonic oscillator? Yeah, 0. It just sits at the bottom. Okay, like right here like this, the energy is 0. Okay? In quantum physics, that's not true, right? If you do quantum physics, then you've all solved this problem. You get some sort of wave function, and the guy's not exactly at 0, right? It's sort of spread out. Because of that spread, you get some extra energy, right? This 0-point energy, we call it. And it's not 0. Okay, there's a little bit of energy here you can never get rid of. This doesn't have any energy at all. So this is kind of interesting, right? This is quite different from the classical case. Okay, everyone is happy with this in normal quantum mechanics, right? Let's go to string theory. Imagine having a closed string, okay? Now, these strings have tension. If you take a closed string and let it go, tension means that the string wants to shrink. In fact, if you look carefully at the equations that you derived for the relativistic string, if you take a closed string and you don't force it to be open, it's going to want to shrink to a point and just collapse into a little point, okay? And this is because the string has a tension, and tension pulls on it, all right? So in other words, the classical lowest energy state for a string is a collapsed state that has zero energy. Yes? Yeah, I sort of tried to avoid going into this in detail. It's a good question. Tension is defined in the following way. The energy of a stretched string is equal to its tension times its length. Okay? That's the normal definition of tension, actually, from ordinary physics. If you think about it, that means the energy is minimized when the string length is zero. This doesn't happen to ordinary strings because most ordinary strings actually don't obey that law, that energy is tension times length. They only obey it once you already stretch them very hard, okay? Relativistic strings turn out to obey that law for all values of the length, okay? It's an excellent question. Okay, but I had hoped to escape from it, but yeah, it's a good question. Okay, but the point is, if you make a closed string and let it go, it will collapse into a point, okay? The energy of this is zero. This makes sense from the particle point of view. You know, there's this formula like E equals to mc square. This formula you should really keep in the back of your mind always. It's the relation between the mass of something and its energy. If the energy is zero, the mass will also be zero. That means the mass of every particle will be zero. That doesn't feel right. That's not correct, right? There are massive particles. It doesn't feel like the right answer, okay? On the other hand, if you do the quantum string, well, what happens then? What you expect is that it won't quite collapse to a point, right? Just like the harmonic oscillator didn't quite collapse to that point, the string will not quite collapse to a point. Instead, the string will do some sort of fuzzy, weird quantum mechanical thing, okay? And now if we calculate the energy of this fuzzy, weird quantum mechanical thing, we should get some number, and that number should have something to do with the mass of the particle that we're looking at, okay? This is the right thing to do. And today we're going to do this. We're going to try to figure out how to describe this weird, fuzzy quantum mechanical thing and calculate its energy. Okay, that's the goal of today. Okay, so let's do it. So first, let me just remind you all, how do we go from classical to quantum physics? For example, say you again have that simple harmonic oscillator. It has a coordinate x of t. Let's think about the classical one first. And this x of t, you know, the thing oscillates, it changes with time. To go to quantum physics, what you do is you take this classical degree of freedom and you make it into a quantum operator, okay? Are people familiar with this process of taking the classical thing and making it into a quantum operator? I will try to put a hat above all my quantum operators, okay? So if it has a hat, it's the quantum thing. And this process is called quantization. It's something that we do. And you've all been through this. You end up using this quantum operator. You get a wave function. The wave function does something, blah, blah, blah. All right? So this is the thing that we want to do, except we want to do this for the string. We had this classical string profile. We want to take this classical string profile and quantize it. Okay? So you want to make it an operator with a hat on it. Now there is a correct, honest way to do this. All right? You do something, you start with the action, you go through some stuff, you quantize the action, you get the answer. But we don't have time, so instead I'm going to do it with a trick, okay? Let me explain what this trick is going to be. And again, everyone should go through this honestly from this book that I showed you. But for now, let's do it with this trick. So first, I need to remind everyone of a bunch of things from the simple quantum harmonic oscillator. And this all came up in Beata's lectures from a couple of days ago. Let me just remind you of some of these things. The Hamiltonian of the quantum harmonic oscillator is p squared over 2m plus half omega squared x squared. I'm setting m to 1. Okay? So this is the Hamiltonian of the quantum harmonic oscillator. Now, an important thing is that the commutator of the x operator and the momentum operator is I. This is like the fundamental thing in quantum mechanics, right? So now, how do we solve the quantum harmonic oscillator? You've hopefully all done this. What you do is you define these ladder operators, right? A is x plus IP and A dagger is x minus IP. These ladder operators are the right way to do the quantum harmonic oscillator. And why is that? Well, ladder operators are super nice. The commutator of A and A dagger, so the commutator of the lowering operator and the raising operator is 1. And if you write the Hamiltonian, this Hamiltonian right here, in terms of these raising operators and lowering operators, you get this. H is omega A dagger A plus half. Is this familiar to people? Good. This is like basically the only quantum system we know how to solve. All right, so I'm going to use this to solve the string theory. Okay, let me just remind you, what is the ground state? The ground state is defined in the following way. We call it 0, the state 0, and it's defined in that A, the lowering operator, annihilates it. Okay? So now, if you act with the Hamiltonian on the ground state, well, what happens? The A here kills that part, so this part goes away. The half is left over. So we get that the energy of the ground state is omega over 2. This is that 0-point energy that I told you about. Okay? This is the energy you can't get rid of. It is the energy of the ground state. Okay. So now what else do we do with this? Well, you know, we generate excited states, right? So here we have the ground state. If you act with A dagger, you get an excited state, which I'm going to call 1. Act with A dagger again, you get another excited state. Act with A, you go down. Act with A dagger, you go up. That's why these are called raising and lowering operators. And from doing this, you can generate all these excited energy states, all these energy states. And they're all energy eigenstates. I forgot the hat, sorry. They're all energy eigenstates, because if you act with the Hamiltonian on these states, this A dagger A bit basically just picks up a factor of k, and this half is always left over. This is the energy of all of the excited states in this thing. Okay? Okay, I think all this is very familiar to everyone. Good. Let's discuss something that is slightly less familiar. Okay? When we talk about things evolving in quantum mechanics in time, there are two ways to do it. The Schrödinger picture, where the states evolve, or the Heisenberg picture, where the operators evolve. In the Heisenberg picture, the operators change in time, and the way to figure out the operator at some time, so for example, let me take the raising operator, or sorry, the lowering operator, A. The way to figure out what that operator is doing at that time is you act on both sides with e to the iht, where h is the Hamiltonian. So for example, if you want to figure out what A of t, an operator, is at later times, you just do this thing, and then you calculate what happens using this Hamiltonian. Have people ever done this calculation? Okay, excellent. You know then that what you get is that A of t is equal to A of 0 times a phase factor. Okay? A oscillates like e to the I omega t. Okay. This is the time evolution of the ladder operator. Okay, still everyone is very happy with this, right? Good. Let's think for a second what this means about x. Yes? Oh, sorry, yeah. H bar is 1. Yeah, good. H bar is 1, m is 1. Any other factors that you think should be there, then draw them to my attention. I'll tell you if I set them to 1. But I've set at least h bar and c to 1. I think that's it, actually. Yeah, I've set h bar and c to 1 today. Okay. Okay, good. But indeed, there should be h bars all over the place, yeah, otherwise. Okay. So let's talk about what this means for x, the particle coordinate itself. Okay? Remember, A was equal to, where was it? A is equal to x plus ip, which means that A plus A dagger is equal to x, because these things cancel with some factors. So what we have is that x is equal to root 1 over 2 omega, A dagger plus A. So if I want to figure out how x evolves in time, I time evolve A, I time evolve A dagger. I know how those both evolve. This evolves to the phase plus omega t, this evolves with minus omega t, and I get x of t as the answer. Okay? So this is the time evolution of x hat of t, the operator. Okay. So next. Now we're going to go to string theory. Okay, so let me just flash this on the screen again. Everyone is happy with this? Now let's go to string theory. Remember, the string Fourier expansion that I started with today. This was the solution to the string equation of motion. What does it look like? We have these guys. I called them A sneakily, but at this point they're just Fourier expansion coefficients, and they all oscillate in time in some way. Now what I want to do is I want to make this a quantum theory. I want to go from this operator x to some quantum operators. So here's the first thing that you have to do to believe me. You have to believe me that the correct thing to do is just immediately make everything an operator without changing anything. Okay? In other words, this equation just works with everything an operator. That should seem plausible because it's normally the case in physics, but you have to believe me because I have not proven it to you. But just believe me now. Okay? Okay. So now we've done it. The quantum theory, we have x, which is an operator. And what is an operator on this side? This is just the length. These are just functions of space and time. So the only thing that can be an operator is the a's. Okay? So the Fourier expansion modes are now operators in this new thing. Okay? So our quantum operators are A and A dagger. What does this remind you of, this thing, where I have A and it oscillates in time? I have A dagger and it oscillates in time. It's exactly the same thing as the harmonic oscillator, right? The difference is that A sub n oscillates with frequency absolute value of n. Whereas here, this thing oscillated with frequency omega. So in other words, these two things are exactly the same if we say that omega in the oscillator is the absolute value of n in the string theory picture. Let me remind you what n was. N was the Fourier mode along the string. So you can make the string oscillate in many different ways. N measured the harmonic of the oscillation. What I'm telling you is the frequency with which this thing oscillates in time is related to the frequency with which this thing oscillates in space. That makes sense, right? That's normal for strings, okay? Even for normal strings. So let me be a bit more precise. More precisely, to describe a string, you should imagine many different harmonic oscillators, one harmonic oscillator for each frequency, for each mode of the string. Okay? The frequency of each oscillator is the absolute value of the wave number. So for example, this is one oscillator. It has a certain wave number. It has some frequency here. This one has a higher wave number, so the oscillator that it corresponds to will have a higher frequency. All right? Okay. And here, again now, there are a few things where you have to believe me. This should seem plausible, though. It's many harmonic oscillators, which means the Hamiltonian for the whole string should be a sum over all of these oscillators. Okay? So for each oscillator, we have one A dagger A. The frequency is the absolute value of n, so we have an n over here where the frequency used to go in the simple harmonic oscillator. Okay, now there's a little bit other stuff going on. Let me just remind you. This string can oscillate this way and this way. It can oscillate in every transverse direction. So I also have a sum over transverse directions here. So I sums over every transverse direction of the string. And finally, there's one more thing. In the simple harmonic oscillator, I had a plus half, right? It turns out the plus half works differently for the string. Instead of having a plus half for each mode, if you sum the plus half over each mode, you end up getting minus 1/12 for each dimension. This might surprise you a lot, because how can you possibly sum half over a bunch of stuff and get minus 1/12? And that's a very good question. And I don't have time to tell you, sadly, but it's an interesting thing. The real issue, let me just tell you what the physics is. The truth is, the constant appearing in the Hamiltonian needs to be determined by other physics. Okay? So what you do is you demand that the physics work out so that the relativistic invariance is preserved. If you do that, it turns out that that fixes this to be minus 1/12. There's also a fun heuristic way to do it. If you look in the string theory literature, people will often say the following formula. They'll often say 1 plus 2 plus 3 plus 4, blah, 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 which is obviously infinity, is equal to minus 1/12. what on earth do they mean by this obviously wrong formula? You can give it a precise mathematical meaning that has to do with the zeta function. And I really wanted to talk about this, but after writing this, I realized there's just no time. So ask me afterwards if you want to know about this, okay? But you have to just believe me for now. There's a minus 1/12 there. Okay, that's the right number. Okay, good. At this point, are there any questions about this formula before I move on and use it to do something? Okay, excellent. Okay, this is what we need to go on. So let me now get into a few more details of how this should work. The string is many harmonic oscillators. Let's put all those harmonic oscillators in their ground state, okay? Then we have something, I'm going to call it the state 0. It is the minimum energy state of the string. It has some energy, okay? We can calculate it. If you have more excited states, okay, like say you act with the raising operators on this thing, this quantum mechanical string will oscillate in some different way. Those things will have more energy, okay? These pictures are getting kind of stupid, I'm sorry, but you get the idea. It's like some sort of higher harmonic, and it's got some sort of structure in this direction, but it's, you know, it's oscillating in some complicated quantum mechanical manner. Okay? So for example, if I act with these two, the ends tell me how rapidly it's oscillating around, the I's tell me in which direction I'm making the string oscillate. Okay. But remember this basic formula that E equals to mc squared. What that means is if we increase the energy, this string is going to look, if you look from a great distance, the string looks like a particle. Increasing the energy means that we are also increasing the mass of the particle that this string looks like. Okay? This should again sound vaguely plausible. And now, again, I have to ask you to believe me. I'm sorry. There's a formula that relates these two things. And the formula is that m squared of the stringy thing, the particle the string looks like, is equal to 1 over the string length squared times the string Hamiltonian that I showed you previously. This is not exactly the same formula as this, all right? It's just not, all right? And again, this has to do with details of how the string theory and relativistic invariance work, all right? You should note they're not the same, right? H is like E, but here I have E equals to M, here I have E equals to m squared. They're really quite different. And again, there's just no time, but there's a way to derive this formula, okay? Okay, so for now, I have to again ask you, please believe me, this is the right formula, okay? Okay, but now that we have this formula, let's use it to find the mass of this stringy thing. So I'm now going to take the string and look for something that I like in it and calculate its mass, okay? So in particular, I started this thing by telling you that there was a way to make this string oscillate that looks like the graviton, okay? Let's look for the graviton in this string oscillation. We actually have all the tools we need to do this part honestly at this point, okay, if you believe all these formulas. So first of all, remember from Anne's lecture yesterday that a graviton was what she called a quadrupole, okay? So what does she mean by that? What she means is the graviton was a particular component of this metric tensor. It affects space and time in various ways. As a gravitational wave goes through, it squeezes space and it squishes space. It does lots of things. But she stressed the following thing, that it was a quadrupole, which meant that it coupled to things in a way that involved 2 x's and 2 y's, or 1 x and 1 y. Do people remember this from yesterday's lecture? Okay. So you should distinguish this, for example, from a normal vector, because a vector is not a quadrupole, it's a dipole. It has just 1 index, okay? This has 2 indices, so it's like axy or something like that. So in other words, how can we make a quadrupole degree of freedom from this string theory? We have to make the string oscillate in at least 2 different directions to get this xy structure, okay? Let's look for the lowest energy state that has the string oscillating in at least 2 directions. So how do we do that? It turns out the lowest energy way to do this is to take A and act with A 1x and act with A minus 1y on the vacuum. Okay. Let me just explain this a little bit. The x and y here are the directions the string is oscillating in. I'm calling those directions x and y. The 1 and the minus 1 are the harmonic along the string. So 1 is the lowest non-zero harmonic. Okay? Minus 1 is just like 1, but the other way. Okay? And it turns out that's the right thing to do here. I'm sorry for making you believe me, require you to believe me so much, but this turns out to be the right thing to do. So the point here is that if we excite the string in the following manner, like AX dagger, AY dagger, or AX, AX, AY, AY, this one is like that one, this one is like that one. If we excite the string in these ways, these guys, these oscillations of the string should be gravitons. Okay? So let's now calculate, using those formulas, the mass of the graviton. Okay? I'm going really quickly, so let's pause here for a second. Does anyone have any questions about this before I go on? Yes? They do, yeah. We're not going to derive that, but they do. Yeah, you can show it, yeah. Yeah, they lose energy up to a point, and then at some point they, like basically, anything that is, let me explain this carefully. Not all particles radiate gravitons. If a particle is at rest, it will not radiate a graviton. It depends if it's excited or not. So if you sort of force it to be excited in some way, then it will radiate gravitons. But eventually it will stop and relax into some sort of energy eigenstate. We're calculating the masses of those energy eigenstates after they've already radiated gravitons. So I think my answer to your question, your first question, was wrong. Not everything radiates gravitons. Only things which are oscillating in some particular quadrupole manner will radiate gravitons. This guy actually is the lowest energy state that will not radiate any more gravitons. That's the correct answer to your question. I didn't understand it at first, sorry. Yeah. Oh, of course. They're going to be disappointed. Hello, Gaza. I don't think this really helps that much, but yeah. Okay, good. Any other questions before I move on? Okay. Okay, so I just want to point out we have all the tools we need to calculate the mass of these states now. So let's do it. Okay, I'm going to calculate this one, and the other one turns out to be the same. Okay. Okay. So what we do is we use the formula I put on the previous slide, where, let me just show you that formula again. The mass is 1 over L string times the Hamiltonian, and the Hamiltonian is this complicated thing here. So it means the mass is 1 over L string times this. Okay, so the mass squared is 1 over L string times this thing. Okay, so now let's calculate it. So first up, we sum over all of the oscillator modes, okay? But the only oscillator modes which are not in their ground state are the 1 and minus 1 modes, okay? We have 1 in the x direction and minus 1 in the y direction. Each of those are 1, so we get a factor of 1 from the x and a factor of absolute value of minus 1 from the y, which is also 1, okay? So we get plus 2 from here, this bit. Okay. Are we done? Well, not quite, right? We have this minus 1/12 that I asked you to take on faith. This minus 1/12 contributes. How much does it contribute? Remember last time I asked you, okay, so now at this point, let's remember, we're string theorists, so we work in an arbitrary number of dimensions, d. Last time I asked you, how many transverse directions are there if we are in d dimensions? And you all told me, d minus 2. That's why we have this minus d minus 2 divided by 12 here. Okay? So the mass of this whole state is 1 over L string squared times 2 minus d minus 2 over 12. Okay. What is the correct answer for this? What should the mass of the graviton be? Anyone? 0. Is it 0? Yeah. So the mass of the graviton is instead 1 over L string squared times 2 minus d minus 2 over 12. This is very disappointing. It seems that it doesn't actually work unless d is equal to 26. If d is equal to 26, it works. The mass is 0. So this is very confusing because it's good. We found the graviton. Okay, the graviton is there. All right, it's right there, but its mass only works out to be the right number if d is 26. Okay, so at this point, I want to discuss what this means. Okay, to have this sort of thing is when I encountered this computation, I was like, this is the first time this has happened in physics to me, that I need the dimension to be something for life to work out right. Okay, so what's really going on? This is weird. And let me say a few more things about what's weird about this. You can go through a lot more stuff, okay? And it turns out that if d is not equal to 26, a lot of other things go wrong, okay? It's not just that this mass is offset from its value. The theory is no longer relativistically invariant. It's very odd that this can happen. You start with a theory that is relativistically invariant. You do quantum mechanics. At the end of the day, it's not relativistically invariant anymore, okay? This is very confusing, but this is a thing that happens in string theory. I see many questions. Okay, yes, question. Yeah. Good. If you did the calculation trying to look for the photon comes from an open string excitation, not a closed string excitation, so it's a different calculation. But if d is equal to 26, the photon's mass is 0. Yeah, okay? If d is not 26, it's not 0. So nothing works if d is not 26, basically, okay? Yes? Oh, sorry. If you set h bar and c to 1, then a mass has the same units as an inverse length, interestingly enough. In reality, this is something like, I can't do it in my head, but you can put back the c's and the h bars and it will work out. It's like mc squared equals to h bar, yeah, I can't do it, yeah, but you get the idea. mc squared is like energy, and energy is like h bar omega, like 1 over frequency, and time is like c times space. So by using h bar and c, you can make all the units work out. Okay. Yes? I'm getting there. The question was, how can we distinguish fermions and bosons? I'm going to get there. I'll mention that. It's a good question. Okay. Okay. So there are many questions here. And how am I doing? Okay, I'm doing fine. Okay. But let me just tell you what is happening. If d is not 26, nothing works. Okay, it's a disaster. All right, nothing makes any sense. If d is 26, then the mass of the graviton is 0. And actually, lots of other things work out as well. The relativistic invariance, which I claim goes away, that comes back. Okay, it's there. The theory is relativistically invariant. There's this excellent suggestion which you should calculate the photon mass. You do that using open string theory and not closed string theory, but you get its number. It's 0 independently from this if d is equal to 26. If d is equal to 26, most things seem to work out. There are still a few things that don't, but we can discuss those afterwards. Let me not get into them. Okay? Okay. So this is weird because it seems like we're getting what we want if only we lived in 26 dimensions. Except not quite. Okay? Because I have been talking about so-called bosonic string theory. And the way to understand that is just that there is no I didn't say the word fermion even once yet, right? Okay? There are no fermions, it turns out, in this thing. Every particle that you get from this sort of stringy thing, none of them will be fermions. But as you pointed out, we have fermions in real life, so we should change the theory to include fermions. Okay? So let's do that. Or rather, let me tell you what happens if we do that. Okay? This was the bosonic string. This is the first chapter of most string theory textbooks. But now in real life we have fermions. If we add fermions, things change. Okay? Their factors are a little bit different. You have to add a couple more things up. And what you find at the end of the day is instead of d equals to 26, you find instead d equals to 10. Okay? This is the famous number that is thrown around. Have people heard this? String theory only works in 10 dimensions. This is what they mean. Okay? The string theory with fermions, it's called superstring theory. That only works in 10 dimensions. Okay? And in 10 dimensions, everything is great, but that's still not the right number of dimensions. Okay? Okay, questions? Is there a question? No. Okay. Okay. So this is better. All right. It's better by 16, I guess, but it's still bad. Okay. Yes. So the question was, 10 is bad. Why am I saying that? What is my expectation? So yeah, I want there to be 3 space dimensions and 1 time dimension. So I would have been very happy if this had worked out to be 4. Okay? You can imagine the people doing this calculation for the first time. They must have thought they made a mistake, right? I'm sure they did it a million times, checking every factor, thinking, okay, it must be 4, it must be 4. But it's really not. It's really 10, okay? Yeah, anyone who's done a long calculation and been off by a factor at the end of the day can really appreciate how painful this must have been for these poor guys, okay? But it's really 10, okay? So I want this to be 4. This is an issue, yeah. Yeah, the way I'm doing it, they're all spatial dimensions, yeah. I actually don't know what happens if you make more than 1 time dimension. This is a recurring question in this school, I think. I don't know what happens, yeah. You could study it, I think. Yeah. Good. Other questions? Okay. Good. So this is better, but this is still bad. Okay, so now what do we do? How do we make sense of this? So we have 6 extra dimensions to deal with. Okay. Now, here's something you can do. If you have an extra dimension, so for example, here I have a 2-dimensional piece of paper. Suppose I want to make this 2-dimensional piece of paper into 1 dimension. I have 1 extra dimension to deal with. This is sort of a very obvious thing to do, right? Which is I should roll it up into a tight little bundle, and then don't look too closely at this direction. And now, from a great distance, it looks like a 1-dimensional thing, right? So in other words, if you just curl up your extra dimensions very small, then you can get rid of them. Okay, so that sounds all right? Let's just do that. Let's take our 6 extra dimensions and let's just curl them up really small, and that should be fine. Okay? So this is something that people actually do. This is an active field of study, all right? But let me tell you what happens if you do this. The issue is that if you have 6 extra dimensions, there's only 1 way to curl up 1 extra dimension. But there are many, 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 many ways to curl up 6 extra dimensions, okay? People tried to estimate roughly how many of those are quasi-reasonable, and the estimate they got was 10 to the 500. That's a ridiculously large number, okay? The point is, each of those solutions, each of those ways to curl up the dimensions, it looks different at low energies, at long distances, by which I mean the spectrum of particles that you calculate is always a little bit different. It's a little bit off. The masses vary, the couplings vary, all sorts of things change. They always have a massless graviton. You can set them up so they always have a massless photon, but other stuff, the quark masses, things like this, all this stuff can change, okay? So in fact, the way that you would really think about this is, if all the particle masses and all that stuff is different, you're really tempted to call this a different universe, right? 'Cause it's nothing like R1. The Higgs mass is off, the quark masses are off, everything will be different. So therefore, the fact that there exist mathematically many solutions to these equations, some people like to say that this means string theory allows for a set of different universes, okay? Many different universes. The word multiverse is often thrown around to discuss this fact that there are many, 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 many different solutions to string theory, each of which have a different particle spectrum, okay? So now the real question is, within this 10 to the 500, is our universe actually there within that set? People have found many, many solutions which are very close. As far as I know, no one has actually found exactly our universe. And this is a very difficult thing to do, actually. There are good reasons to think that finding exactly ours will be very hard. Okay? So this is sort of where we stand. We solved the problem that we started out to solve. We solved the problem of quantum gravity. I did not prove to you that we solved it at all, but I argued to you how to look for the massless graviton in this theory. Okay? But we now have a different set of problems. There are now many different solutions. We have to find some way to isolate our universe from this set of solutions in a way that makes us happy. And I think it's fair to say this has not been done yet. Another possibility is just that this way of thinking about string theory was not quite correct, you know. I explained it to you in one way, but many of us, including me, think that there's probably a better way to think about string theory than this. A lot of things here are kind of random. It seems weird to add 6 extra dimensions to get something to work out, then curl them up again just to get that to go away. You know, this seems weird. There's probably a better way to formulate it where that step was not necessary. But I don't know what that way is, and I think it's fair to say no one knows what that way is. Okay. So let me conclude. My conclusions are the following. Number one, quantum gravity is hard. The reason why it's hard is basically because everything feels gravity, and this means we have too many gravitons at short distances. String theory helps. It solves that initial problem of quantum gravity being hard. It gives us a fully consistent quantum theory that has the graviton in it. We actually check that. And if you pick the dimension to have the right number, the graviton is massless and everything works. By everything works, I should really tell you a lot of stuff happens that makes a lot of sense, okay? Everything you expect from quantum gravity happens in string theory. The structure of space-time fluctuates. You can have wormholes, black holes are formed, they evaporate. You can count the black hole entropy. Hawking radiation, which Anne talked about, that happens. All these things happen in beautiful ways, but the number of dimensions is different. And there are other issues as well. And what that means is really, we're not done yet. We still have lots and lots of work to do. And that's hopefully where all of you will come in. Thank you. Okay. Questions? Yes. Excellent question. Let me repeat it so they can hear you in Gaza. The question was, when I wrote this down, I chose only two particular modes, 1 and -1, right here. Why not the other ones? You can do the other ones. Let's do them really quickly. Sorry, this is the formula I need. Let's do A2 AY minus 35, okay? What do I get from here? I get a +2 because n is equal to 2, and I get a +35 because, well, it's minus 35, which means I have a 37 left over here, which means no matter what, this thing will not be big enough to cancel it, so I'll get a +37 here, which means I will have a particle whose mass is roughly 1 over the string length squared times 35. The string length is really, really, really small. That mass is really, 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 really big. And you can probably ignore that for most things. Okay? So that's why I didn't think about it. But it exists. There's an infinite tower of particles going up to infinity with masses that are spaced in this way. Okay? Yes? Yeah. That's a good question. The question was, I said there'll be a disaster if the graviton had a mass. What is that disaster? So I'm just going to tell you what happens, and I can't really justify this. You see, the question, another way to formulate that question is, why is the graviton massless? What does that mean? And it turns out what that means is that this is closely related to relativistic invariance. If you want a theory where your coordinates don't matter, okay, where you can rotate your coordinate system and the physics is invariant under that, if you want that, the graviton has to be massless. Okay? These two things are related to each other. It's something called diffeomorphism invariance or gauge invariance. Okay? These two things are related. If the graviton is not massless, you tend to lose that thing. You lose that property. And another, maybe a better answer, so that was a theoretical answer. Now, an experimental answer, we have detected gravitational waves and measured the speed of light to 1 part in 10 to, sorry, the speed of gravitational waves to 1 part in 10 to the, what was the number? 10 to the 15, 10 minus 15. 1 part in 10 to the 15, it's equal to the speed of light. That means the mass of the graviton is 10 to the minus 15 times something. So it's experimentally, it seems to be 0 as well, okay, which is good. Everything here is consistent. Okay, excellent. Good. Yes, question in the back. Can we, yeah. Maybe we can you give the microphone there, because I feel like I'm not repeating the questions correctly. Thanks.
Hello. As I understand it, the string has its oscillation. So can we create more than one wave in the same string?
Absolutely, yeah. So in fact, this one right here that I'm looking at, you should think of this as 2 waves on the same string. Okay? This one is the string oscillating in the x direction. There's a couple of things going on here. So I have my string. I make it oscillate in the x direction, and the wave goes around like this. And I make it oscillate in the y direction, and the wave goes around the other way, because it's -1. Okay? So there are actually 2 waves going down this string in opposite directions right now.
So the waves can be constructive or destructive from? How can we make sure that they will not be destructive?
All of that is happening actually already. In this formula, all the waves are interfering because we sum over all of these modes, you see? So they're all interfering just by normal Fourier analysis. They will never be exactly constructive and destructive because the Fourier modes are orthogonal. So they'll never exactly cancel out, but they all oscillate and ripple in some sort of way. Yeah, it's a good question.
Thank you, thank you.
Okay. Other questions?
Some questions from Gaza.
Okay.
So my laptop's dead, so I have to do
Okay.
here.
Or we could call them from mine, or is this working? Hello? Hello. Hi, are there some questions from Gaza? Can they see me? Maybe not. Hello? Can you hear me? Oh, nope. Hello? I think it was working, but hello? Hello? Okay. Hi. Okay. So there are some questions from Gaza?
Yes.
Okay.
I'm not sure. Can you hear me?
Yes, I can hear you.
So my question is, our universe is not one of the possible answers of the string theory or possible solutions.
I think that our universe is one of the possible. Sorry, let me repeat the question. The question was, is our universe one of the possible solutions to string theory? And I'm saying, yes, it is possible, but no one has explicitly constructed exactly our universe yet. I see no reason why it's not possible. We get closer all the time, but no one has written down the exact one that's ours. Yeah.
So the actual question is
Oh.
based on what we identify, like this, based on what we identify that our universe fits with the characteristics of the solution.
Very good. This is an excellent question.
What's the characteristic that identify the
Yeah. I think I understand. I believe the question was, what are the characteristics that we use to identify our universe within this set of solutions? Like, what is it about our universe that makes us think it's going to work out, or something like that? So that's a very good question. So here are a few things about our universe that people look for when trying to build the string theory description. So for example, we have quantum gravity. The graviton is exactly massless. Okay, that's good. The spectrum of particles is kind of interesting. The way in which particles interact in the standard model of particle physics is through gauge fields. Okay? The structure of those gauge fields has information. It's the same sort of thing that we can get from string theory. Okay? There are things called chiral fermions. People might have heard of these. The fermion couplings are interesting in that the left and right-handed fermions couple differently. That kind of thing is consistent with string theory and can be gotten from string theory. There are a few things that if you get them, you know that you don't have a string theory. Okay? They're a bit technical. They have to do with the signs of various interaction terms and things like that. None of those have been observed. Okay? If we had observed one of those, we could immediately say string theory does not describe our universe. Okay? But none of those have been observed, and I think that none of them will be observed because I think those things are all really weird. So basically, there's nothing that really tells us that string theory does not, sorry to say this, I am not aware of any fact about our universe that prevents it from being a solution to string theory. But I should tell everyone, why is this problem so hard? Like, why can't we find our universe? It seems like an easy thing to do, right? The reason why this is so hard is because the things we talk about when we talk about our universe are much, much, much longer than the Planck scale. It's kind of like, imagine you sort of live in water, okay? And like you're living in this water and you're all happy, and then some sort of atom theorist comes and says, hey guys, I know what's happening. The world is made of atoms. And you live in this water and you're like, well, prove it. And he's like, well, I can't really prove it. I think it's true for some sort of deep reason, but I can't prove it. And he's like, well, just find the water from your atom theory. They're going to have a lot of trouble because it's very hard to prove the existence of water from the standard model, from like particles. It's really difficult to do that. And that problem is the same problem that we face right now. It's very hard to take strings and assemble them together to get particle physics. For the same reason it's hard to take particles and assemble them together to make water. It's because lots of stuff happens in the way. And it's hard to solve everything all the way through. Okay. Okay. Good. Other questions?
So about the other universe, about
Yeah.
other universes, what are the differences? Like the other universes that comes as solution, what are the differences from our universe? What distinguishes them?
Very good. The question was, what distinguishes the other universes from our own? So there are many things that can be different. The particle masses could be different. The number of dimensions could be different. One very important thing which will be different is the cosmological constant, which Anne talked about, is probably going to be different in all these other universes. That's a huge difference right there. Okay? Ours is a very special value. That number, there's no reason for that number to be the same. It'll probably be very different. And that will change everything dramatically. Okay? That's a good thing. Okay. Good. Any questions either from Gaza or from here? Okay. If there are no other questions, in that case, let's call this to a close and take a brief break. Thank you. This is the old one. No, it's not. Wait, hang on. This is an old one. That would have been awkward. How did I even find an old one?
Oh, I think I saved it as it's in, yeah.
Sorry?
Do you have a presentation for the end?
Yeah, we do. Yeah.
We'll zoom on it for now and we'll change it.
Yeah.
Okay, lectures, right? Oh, no, sorry. What am I doing? It's in here? Yeah, okay.
No, it's like,
No, it's not this one. I think it's a different one. It's lecture files. Here we go. Lectures, closing. This one. This one?
yeah.
Okay, perfect. Cool. Okay. Okay. All right.
Do you want me to read the names?
Uh,
Arabic?
or should I do it awkwardly? Is that fine, or you think it's bad?
Yeah,
You want to
no,
read
it's
them? Okay. Yeah. Do they mind? I did it last
No.
time. Yeah. I don't know. Yeah.
I don't think they'll mind.
They don't mind, right? Okay. Some of them I know because many of them are sort of in Bangladesh as well. The pronunciations are a bit different, but yeah. Is that okay? All right. Okay. All right. Cool. Oops. Okay, let's get started. And we'll come here and take a picture there and go on. Yeah. Okay. Sorry. Okay. Hello, everyone. I hope everyone is here. Okay. Okay, so this is a mildly sad occasion because this is the end of the Palestinian Advanced Physics School 2019. Oh. Okay. So we're about to begin. So let me just remind you what happened over the last 5 days in case you forgot. What we basically did was we learned a lot of physics. You sat through many lectures. You worked in discussion sessions. You met lots of fun people. Hopefully you thought it was fun as well. And we all talked and hung out and learned lots of things. And indeed, our colleagues from Gaza who could not be here in person, nevertheless, followed extremely closely everything online. So let's... So at this point, yesterday, you all handed in homework that you worked on very hard over the last week. As we promised, everyone who did the work gets a certificate of attendance to celebrate this. So what's going to happen is, I'm going to read your name, and then you come up over here, and you'll receive your certificate from, let's do it. I'll pass it to Hannah, who will give you your certificate. Okay. So in alphabetical order, we have Ali Amria. Ali Takatka. Ali Manasra. Anas Jude. Asila Mustafa. Not here? Okay. Poor Asila. Aya Nasar. Not here. Oh. Okay. Farid Talba. Fatima Sabatin. Hana Bashir. Outside. pause for 1 second, yeah. Shall I continue? Okay, if I get to him, I'll pause, yeah. Khalida Awashra. Khattab Abu Al-Rob. Kinan Al-Namura. Laith Marzuka. Not here? Okay. Mariam Mutan. Muhammad Hamshari. Muhammad Abu Allan. Muhammad Abu Allan, he's here, right? Yeah. Muhammad Raddad. Not here. Moritz Gunther. Okay, we'll come back. Muat Hamidi. Nancy Muhammad. Nida Al-Bader. Come on, Nida. Okay. Obada Nairat. Omar Al-Farouk Obidieh. Rami Masri. Rami is here. Okay. He can get his later. Rand Akra. Rashad Hamidi. Ryan Abdul Hadi. Rula Bakir. Salma Braik. Sarah Abu Zayed. Sarah Akel. Shruk Naruk. Wafa Ayaida. Wala Tseo. So let's have one more round of applause for everyone from the West Bank who came to the school. But no less were the participants from Gaza who could not be here in person. So let's now try to bring them onto the screen so we can give them their certificates. Hello. Okay.
Yes, Dr. Nabil.
Yes.
I think you can call the student Doha. And hello.
Hello. Which student? Doha. Okay. Yep. Hello. Hello, Doha. Okay. So, are you ready? We're going to put you on the main screen so everyone can see you. Okay. So you'll be on the main screen in a second. Okay, you're on the main screen. I will now read out the student names, and hopefully you can show them on the screen when I read them out. Are you ready? Okay, so I'm told that some are not here, but we will do our best. Okay, ready? Zuhair Abughali. Can you hold this next to the thing? Zuhair, we have Zuhair? Okay. Yes, Zuhair Abughali, everyone. Yes. Okay, next. Salahuddin Elayan. Salahuddin, sorry. Okay. Salahuddin. Hello. Okay, next. Oh, waiting for Salah. Oh. Okay. Okay. We will continue, and maybe we can come back. Yeah. So. Okay. Okay, so now let's go on and just thank all the people who made this school possible. So a brief pause for some acknowledgements for people who traveled far to be here. Most of them are no longer here today, but we should thank them in any case. So, first of all, Anne Christine Davis, who told us about the structure of the universe at the largest possible scales. Beata Kardynal, who told us how quantum optics can be used to probe the structure of entanglement. And finally, Rafal Dunin-Borkowski, who explained to us the structure of electron microscopy. We would also like to thank the following people. Abdallah Sayyed-Ahmad for arranging everything from this side. Galib Natur for organizing the coordination of the PGSP. Sameh Othman, who is a hero in every sense of the word. And finally, Sami Shath, who organized everything from the Gazan side. And finally, I just want to say a few more words. This is the third time that we are doing this, and every time we are here, I always remember that the fun part of physics, you know, it's very fun to quantize the bosonic string and to study electron microscopy and cosmology and solve all these equations. That's all really fun. But honestly, the part that is the most fun for me personally is to talk about physics to people who are as enthusiastic and as energetic as all of you. So thank you for making this the most fun physics experience that I've ever had.
On behalf of all of us, we want to thank you, Nabil, for everything and all of help during this school. Thank you so much.
Thank you. Okay, so that is officially the end of the school. So here's what will happen now. There is lunch coming soon. Some of us have to have meetings with some people at the university, but we will be back shortly after that, and I would love to hang out with you and eat lunch in a little while. So food is coming, yeah? Food is coming. Okay, so everyone hang around, have fun. We'll be back. The food will be back as well. Okay, thank you, everybody.